Semiconductors are materials that are not full conductors like copper, nor full insulators like rubber. They fall in between, which makes them very useful in electronics. The idea of semiconductors became important in the early 20th century, but the real breakthrough came in 1947, when the transistor was invented at Bell Labs. This small device replaced bulky vacuum tubes and revolutionized electronics. Later, integrated circuits, ICs, in the 1960s allowed thousands of transistors to be packed into a single chip, making computers smaller, faster, and more affordable. Semiconductors usually use silicon as the base material. By adding tiny amounts of other elements, a process called doping, engineers can control how electricity flows through them. This makes it possible to build transistors, diodes, and microchips that form the brains of modern electronics. Semiconductors work based on how electrons move inside the material and how engineers control that movement. In physics, materials have energy bands where electrons can exist. In conductors, like copper, electrons move freely. In insulators, like rubber, electrons are stuck. A semiconductor sits in between. Electrons can move, but only if they get enough energy, like from heat, light, or electricity. To make semiconductors useful, engineers dope them. Adding a very small number of atoms of another element, this creates two types. N-type, extra electrons are available. P-type, there are holes where an electron could fit. When P-type and N-type semiconductors are put together, they form a p-n junction. At this junction, electrons and holes meet, creating a region that can control current. This is the basic idea of diodes, which let current flow only one way. By arranging many junctions, we get transistors, which can act as switches or amplifiers. Billions of these tiny transistors can be connected together on a silicon chip. By switching on and off incredibly fast, they process information, the foundation of computers, smartphones, and modern electronics. In short, semiconductors work by controlling the flow of electrons using doping and p-n junctions, and when combined in huge numbers, they become the powerful chips we rely on every day. A diode is one of the simplest and most important applications of semiconductors. A diode is made by joining p-type and n-type semiconductors into a p-n junction. When you connect them, a special boundary is formed that only allows current to flow in one direction. Forward bias, current flows, if you connect the positive side of the battery to the p-type and the negative side to the n-type, the barrier inside breaks down and electrons can move. Current flows. Reverse bias, no current. If you flip the battery, the barrier becomes stronger and no current flows. The diode acts like a one-way valve for electricity. A transistor is essentially a semiconductor device. It couldn't exist without semiconductors. A transistor is a tiny switch or amplifier made from semiconductor material, usually silicon. It has the ability to turn current on and off, or to increase, amplify a signal. The magic comes from how semiconductors can be doped to create N-type
extra electrons, and p-type, holes for electrons. By carefully combining these regions, engineers can build structures like PNP or NPN junctions. These structures allow the transistor to control a large current with a very small input signal. Think of semiconductors as the raw material, like clay, and transistors as the objects sculpted from it, like bricks. By combining billions of these bricks, we build computers, phones, and modern electronics. All right, let's go step by step and see how a transistor works like a switch. Imagine a transistor has three parts: base, control gate, collector, input side, emitter, output side. Think of the base as a little gate that controls the flow between collector and emitter. If no voltage is applied to the base, the path between collector and emitter is blocked. This means no current flows, like a light switch in the off position. If you apply a small voltage to the base, it opens the path. Now a much larger current can flow from collector to emitter. This is like flipping the light switch on and letting electricity power the bulb. Interestingly, the small input at the base controls a much larger output. This means a transistor isn't just a switch, it can also amplify signals, like making a weak microphone signal strong enough to drive speakers. Semiconductors start with pure silicon. Engineers grow large single crystals of silicon, called ingots, then slice them into thin disks known as wafers. To control how electricity flows, tiny amounts of other elements, like boron or phosphorus, are added to the silicon. This creates p-type and n-type regions. This is like printing tiny patterns on the wafer. Engineers coat the wafer with a light-sensitive material, shine UV light through a mask, and etch away unwanted parts. Etching, removing material where it isn't needed. Deposition, adding thin layers of metals or insulators. These steps build up the layers that form transistors and circuits. Oxidation and insulation. Silicon can be oxidized to form silicon dioxide, SiO2, which acts as an insulator. This is crucial for separating different parts of the circuit.
Once transistors are made, they must be connected. Engineers use metals like copper or aluminum to form the wiring that links billions of transistors together. Finally, chips are tested for performance and defects. Good ones are packaged into protective cases and mounted into devices like computers and smartphones. Miniaturization limits. Pushing transistors below 3 nanometers faces quantum effects and leakage currents. Extreme manufacturing costs. Advanced chip fabs, like EUV lithography plants, cost tens of billions of dollars. Material challenges. Silicon is reaching its limits. New materials like GaN, SiC, and 2D materials, graphene, are needed. Heat management. Smaller transistors in higher density generate more heat, making cooling harder. Supply chain risks. Global dependence on a few regions, Taiwan, South Korea, creates geopolitical vulnerabilities. Design complexity. Chips with billions of transistors require advanced AI-assisted design tools. Power efficiency. With more devices, IoT, AI servers, reducing power consumption is critical. Yield and defects. As chips shrink, even tiny defects can ruin entire wafers, lowering yield. Talent shortage. A lack of skilled engineers and scientists slows innovation in semiconductor R&D. Environmental impact. Chip making consumes vast amounts of water, energy, and chemicals, raising sustainability concerns. EUV lithography limitations. Even extreme ultraviolet machines struggle to etch features below a few nanometers with high accuracy. 3D integration challenges. Stacking chips, 3D ICs, increases performance but complicates heat dissipation and manufacturing. Defect detection at atomic scale. It's increasingly hard to spot and fix tiny atomic-level defects during fabrication. Equipment supply bottlenecks. Few companies, like ASML for lithography, dominate key equipment, creating supply risks. AI and HPC demand pressure. Explosive growth in AI training and high-performance computing demands chips beyond current limits. Heterogeneous integration. Combining different chips, CPU, GPU, memory, into one package is complex but necessary. Cybersecurity risks in chips. Hardware-level vulnerabilities, like Spectre meltdown, show chips can be attacked directly. Global competition and subsidies. Countries are racing to build fabs and offering huge subsidies, creating economic tensions. Testing complexity. Verifying chips with billions of transistors is enormously complex and time-consuming. Quantum effects at nanoscale. As transistors shrink, electrons can tunnel through barriers, breaking traditional designs. Chiplet integration. Moving from one big chip to many smaller chiplets introduces new packaging and communication challenges. Reliability over time. Devices must last years, but aging effects like electromigration and oxide breakdown degrade chips. Radiation and cosmic rays. At small scales, stray particles from space can flip bits in memory or logic circuits. Analog-digital integration. Combining precise analog circuits with dense digital logic on the same chip is increasingly complex. Testing at scale. Verifying trillions of operations per second for AI chips is nearly impossible with traditional methods. Resilience to supply shocks. Natural disasters or political conflicts can halt global chip production. Standardization gaps. New packaging, interconnect, and chiplet technologies lack universal industry standards. Edge computing needs. Billions of IoT devices need cheap, low-power chips, creating different challenges from high-end chips. Global competition for talent. Nations compete to attract top semiconductor engineers and researchers, fueling a brain race. 1947, first transistor, Bell Labs. The very first transistor was invented, much larger than today's devices, but it proved semiconductors could replace vacuum tubes. 1958, integrated circuit, IC. The first IC was built combining a few transistors on a single chip, starting the trend of miniaturization. 1971, Intel 4004, 10-micron process. The first commercial microprocessor had 2,300 transistors made with a 10-micron process. 1974 to 1980s, MOSFET scaling. MOSFET technology improved, shrinking feature sizes below 5 micron and pushing computing forward. 1990, 800-nanometer process. Chips reached sub-micron levels, allowing millions of transistors per chip. 2000, 180-nanometer process. Transistors became smaller than a red blood cell, enabling faster and more efficient CPUs. 2004, 90 nanometer and 65 nanometer nodes. Dual-core processors became possible, packing more transistors into smaller chips. 2011, 22 nanometer and FinFET. The 3D transistor, FinFET, was introduced, solving leakage problems as miniaturization hit physical limits. 2019, 7 nanometer and 5 nanometer nodes. Used in advanced CPUs and smartphones, packing tens of billions of transistors. 2022 to 2025, 3 nanometer and beyond. The latest chips, Apple, TSMC, Samsung, use 3 nanometer processes, with 2 nanometer in development, approaching atomic scale limits. In summary, from 10 micron 1971 to 3 nanometer today, transistor size has shrunk by over 3,000 times, enabling the digital revolution. Extreme miniaturization, 3 nanometer to 2 nanometer and beyond. As transistors shrink, quantum tunneling and variability in atomic placement cause unpredictable behavior. Power leakage. Smaller transistors leak current even when off, wasting energy and generating heat. Heat dissipation. High transistor density in small chips creates hotspots that are difficult to cool efficiently. EUV lithography precision. Even with EUV, extreme ultraviolet, lithography, aligning patterns at nanometer scales is extremely challenging. Material limitations. Silicon alone is reaching physical limits. Integrating materials like GaN, SiC, or 2D materials is difficult. Interconnect scaling. Wiring between transistors doesn't shrink as easily, creating resistance and signal delay problems. Reliability at atomic scale. At nanometer sizes, atomic defects or impurities can disable entire circuits. Testing complexity. Verifying chips with tens of billions of transistors for defects requires new automated methods. 3D integration issues. Stacking chips improves performance but worsens heat and manufacturing yield. Power efficiency versus performance. Balancing ultra-high performance for AI, HPC with power efficiency for mobile and IoT is a major conflict. Raw materials. High-purity silicon used for wafers, specialty gases, argon, nitrogen, fluorine, etc., chemicals, photoresists, etching acids, cleaning solvents. Alternative materials. Gallium nitride and silicon carbide for power devices, germanium, graphene, and 2D materials for next-generation chips. Wafer fabrication knowledge. Crystal growth, Krozalski method, wafer slicing, polishing, cleaning. Doping techniques. Ion implantation, diffusion processes. Lithography technology. Photolithography, using light to transfer patterns. EU lithography, extreme ultraviolet, for advanced nodes. Etching and deposition. Dry and wet etching to carve patterns. Chemical vapor deposition and physical vapor deposition for thin films. Clean room and environment control. Class 1 or better clean rooms to avoid contamination. Temperature, humidity, and vibration control systems. Equipment. Lithography machines, ASML EUV scanners. Etching, deposition, and ion implantation tools. Metrology and inspection systems, electron microscopes, defect scanners. Packaging and interconnect. Wire bonding, flip chip, 3D stacking, advanced packaging, chiplets, and HBM integration. Foundational knowledge, solid-state physics, band theory, semiconductors, electrical engineering, circuit design, transistor theory, materials science, defects, crystal growth. Let's go step by step through the semiconductor production flow from raw sand all the way to a packaged chip inside your phone or computer. Sand to silicon extraction. Starting material, silica, SiO2, found in sand. Purified into high-purity silicon, 99.9999%. Crystal growth, ingot production. Using the Czochralski process, a single crystal silicon ingot, a cylinder, is grown. These ingots can be over 300 millimeters in diameter today. Wafer slicing and polishing. The ingot is sliced into thin discs, wafers. Each wafer is polished to atomic-level smoothness. Oxidation and layer preparation. A thin layer of silicon dioxide, SiO2, is grown for insulation. Acts as the foundation for later steps. Photolithography, pattern printing. Wafer coated with light-sensitive photoresist. UV or EUV light shines through a mask, transferring circuit patterns. Etching and doping. Etching removes unwanted material, leaving patterns. Doping adds atoms, boron or phosphorus, to form p-type and n-type regions. Deposition, layer stacking. Thin films of metals, insulators, and semiconductors are deposited. Layers are built up to form transistors, capacitors, and interconnects. Interconnection. Copper or aluminum wiring connects billions of transistors. Multi-layered wiring networks form the chip's nervous system. Packaging and final product. Good chips are cut from wafers, mounted on substrates, wired, and sealed in protective packaging. Packaged chips are shipped to device makers for integration into PCs, smartphones, and cars. A semiconductor is a material whose electrical conductivity is between a conductor, like copper, and an insulator, like rubber. The most common semiconductor material is silicon. Semiconductors are the foundation of modern electronics. They can control the flow of electricity in precise ways. This control is what makes computing and digital logic possible. Electrons in semiconductors exist in bands of energy levels. The band gap determines how easily electrons move. Conductors have no band gap, insulators have a wide band gap, and semiconductors are in between. By adding impurities, doping, semiconductors can be modified to carry more or fewer electrons. N-type semiconductors have extra electrons, P-type have holes. Combining P-type and N-type creates a P-N junction, the heart of many devices. A diode is a P-N junction that lets current flow only one way. A transistor is a more complex device made from multiple junctions. Transistors act as switches and amplifiers. Billions of transistors form the processors in computers and phones. Semiconductors start from purified silicon extracted from sand. Silicon is grown into single crystals called ingots. Ingots are sliced into thin wafers. Circuits are printed on wafers using photolithography. Layers of metals and insulators are deposited to form complete circuits. Every smartphone relies on semiconductor chips. Computers, from laptops to supercomputers, are built on semiconductors. Cars use semiconductors in sensors, batteries, and control systems. Medical devices, like MRI machines and pacemakers, depend on semiconductors. Everyday gadgets like TVs, microwaves, and game consoles contain semiconductors. The first transistor was invented in 1947. Integrated circuits, ICs, emerged in the late 1950s. Moore's law predicted that transistor counts double every 2 years. From 10 micrometers in the 1970s, transistor size has shrunk to 3 nanometers today. The industry now explores 2D materials and quantum devices for the future. Step 1. Foundations, Materials, and Physics. Learn what semiconductors are. Conductors versus insulators versus semiconductors. Understand band theory and the concept of the band gap. Study intrinsic silicon and how doping creates N-type and P-type materials. Explore crystal growth and wafers as the starting material. Step 2. Core devices. Learn how PN junctions form the basis of diodes. Study diodes, rectification, LEDs, protection. Move to transistors, BJT, MOSFET, FinFET, and GAA-FET. Understand how transistors act as switches and amplifiers. Step 3. Manufacturing processes. Photolithography, how patterns are printed on wafers. Etching and deposition to form layers. Doping and ion implantation techniques. Clean rooms, contamination control, and inspection. Step 4. Integration and packaging. Learn about interconnects, copper, aluminum wiring. Packaging methods, wire bonding, flip chip, and 3D stacking. Yield management and defect reduction. Testing methods before chips ship. Step 5. Applications. CPUs, GPUs, and memory in computers and smartphones. Power devices in cars and energy systems. Semiconductors in medical equipment. Everyday electronics, TVs, game consoles, and IoT devices. Step 6. Modern challenges. Miniaturization limits, 3 nanometers, 2 nanometers, and quantum effects. Heat dissipation and power efficiency. EUV lithography limitations. Supply chain and geopolitical risks. Step 7. Future directions. New transistor designs, GAA-FET, and nanosheets. New materials, GaN, SiC, graphene, and 2D materials. 3D ICs and heterogeneous integration, chiplets. AI-driven chip design. Quantum computing and neuromorphic chips. Sustainability, reducing water, energy, and chemical use in fabs. At the most fundamental level,
A semiconductor is about controlling electricity. A transistor, made from semiconductor material, acts like a switch. It can either let current flow, on equals 1, or block it, off equals 0. Billions of such switches are combined to form logic operations. When transistors are connected, they create logic gates such as AND, OR, NOT. These gates process binary signals, 0 and 1. From logic gates, you can build circuits that perform addition, comparison, memory storage, and data transfer. In other words, the building blocks of computation. The CPU is essentially a gigantic collection of these circuits organized to execute instructions step by step. Each instruction is nothing but a binary code, zeros and ones. The memory, RAM, storage, is also semiconductor-based. It holds the data and the instructions that the CPU needs when you open an app. Its code is loaded from storage into memory, ready for the CPU to execute. Now comes the key part: software on hardware. An operating system, OS, is itself just a very large program written in binary instructions. The OS manages hardware, CPU, memory, storage, and I/O devices, and provides an environment where applications can run. Applications, apps, are also programs written in binary, interpreted by the CPU. So yes, at the lowest level, semiconductors are just controlling electricity. But by scaling this up with billions of transistors arranged into CPUs and memory, and by feeding them carefully written instructions, software, we get computers that can run OSs, apps, games, and even AI. For analogy, semiconductors are like water taps, just opening or closing. But when you combine billions of taps in precise patterns, you can control an entire factory's water system. That's how semiconductors become computers. At the lowest level, a semiconductor transistor is simply a switch. It can turn current on, 1, or off, 0.
Billions of transistors form logic gates, circuits, CPUs, and memory, all of which ultimately work only with zeros and ones. Software, whether an OS or an app, is just a long list of instructions written in binary, zeros and ones. For example, one instruction might mean add two numbers or move data from memory to CPU. When you run a program, the CPU fetches instructions from memory. Each instruction is interpreted by the CPU's control circuits, which activate specific groups of transistors. If the instruction is add, the CPU routes data to the Arithmetic Logic Unit, ALU, where transistors perform binary addition. If the instruction is store, the CPU sends signals to memory circuits, writing data as 0/1. The operating system, OS, is a special program that coordinates all these hardware-level operations. It tells the CPU when to run which application instructions, manages memory, and handles input-output. Applications, apps, run on top of the OS. Their high-level code, like Python, C, or Java, is ultimately compiled into binary instructions that the CPU's transistors can switch on and off to execute. Semiconductors provide the physical mechanism, transistors switching electricity. Hardware, CPU, memory, circuits, organizes billions of switches into a system that can process instructions. Software, OS, apps, is written as binary instructions, which directly control how transistors switch. Put another way, software is the blueprint of switch operations, and semiconductors are the machine that flips those switches in real life. You want to know how something like a Python or C++ program eventually becomes binary instructions that flip transistors inside a semiconductor. Let's go through the whole chain step by step. You start with human-readable code, like Python, C, or Java. This is abstract, designed for humans, not for the CPU. Compiled languages, C, C++, a compiler translates the entire source code into machine code, binary instructions, ahead of time. Interpreted languages, Python, JavaScript, an interpreter or VM reads the code line by line and internally calls machine instructions to execute it. Hybrid, Java, C#, source is first converted to bytecode, then executed by a virtual machine, JVM, .NET CLR, which in turn runs on real machine code. The result of compilation is machine code, a sequence of binary numbers, zeros and ones. Each binary instruction corresponds to an operation defined by the CPU's instruction set architecture, ISA, like x86, ARM, or RISC-V. Inside the CPU, special circuits interpret each instruction. Control unit, CU, decodes the binary instruction. ALU, arithmetic logic unit, performs math and logic. Registers and data paths handle data movement. At this deepest level, everything reduces to millions or billions of MOSFET transistors switching on and off. A 1 is represented by a high voltage, opening a transistor path. A 0 is represented by low voltage, closing a path. By orchestrating these switches according to machine instructions, the CPU physically moves electrons in precise patterns, which corresponds to executing software. We're diving into the heart of computer architecture, how a CPU takes a binary instruction, zeros and ones, and turns it into physical electrical changes inside the semiconductor. Let's break it down systematically. The CPU fetches binary instructions, machine code, from memory into its instruction register. The CU, control unit, generates control signals, essentially voltage pulses that direct other parts of the CPU. ALU, arithmetic logic unit, control signals open and close transistor pathways that implement binary addition, subtraction, and, or, etc. For example, adding two numbers means routing currents through transistor networks wired as adders. Registers and data paths. Control signals tell transistors in register circuits to either hold a value or pass it along. Memory access. If the instruction involves memory, transistors in memory controller circuits generate voltages on address lines, selecting specific memory cells. Memory cells themselves are just tiny transistors or capacitors that hold a 0, no charge, or a 1, charge. At this deepest level, everything reduces to millions or billions of MOSFET transistors switching on and off. A 1 is represented by a high voltage opening a transistor path.
A 0 is represented by low voltage, closing a path. By orchestrating these switches according to machine instructions, the CPU physically moves electrons in precise patterns, which corresponds to executing software.
They are the brains of all modern electronics. They act like billions of tiny switches, turning electricity on and off. They make computers possible by processing zeros and ones. They store data in memory chips like RAM and SSDs. They power your smartphone's apps, camera, and internet connection. They run operating systems like Windows, Android, and iOS. They control the graphics in TVs, game consoles, and PCs. They manage signals in cars for safety features and navigation. They are the heart of medical devices like MRI and pacemakers. They enable communication in 5G networks and Wi-Fi. They make energy-efficient power systems, solar panels, and EVs possible. They control household appliances like microwaves and washing machines. They make banking and e-commerce secure through encryption. They allow artificial intelligence to learn and process data. They are essential in satellites and space exploration. They are used in sensors for health tracking, wearables, and smartwatches. They handle sound processing in speakers, headphones, and voice assistants. They coordinate factory machines in industrial automation. They reduce energy waste by optimizing electricity use. They connect the physical world to the digital world, enabling the Internet of Things. If someone wants to work in the semiconductor field, they need to build knowledge in 3 main layers. 1. How semiconductors fundamentally work. 2. How they are manufactured. And 3. How they are turned into real products.